April 30th, 1942. RAF Duxford, England. Ronald Harker settled into the cockpit of the Mustang Mark I, his hands moving across controls that felt somehow both familiar and foreign. As Rolls-Royce's liaison test pilot, Harker had flown most of Britain's frontline fighters. He'd wrung out Spitfires and Hurricanes, evaluated bombers, and mastered aircraft that most pilots would never touch. But this American fighter was something different. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The North American Mustang sat on the tarmac with its distinctive profile, sleek and purposeful. Wing Commander Ian Campbell Ord of the Air Fighting Development Unit had specifically invited Harker to fly this particular aircraft, and the invitation carried weight. The RAF needed answers about this American design, and Harker's employer, Rolls-Royce, had a vested interest in understanding what made this fighter tick. Harker advanced the throttle. The Allison V1710 engine responded with its characteristic roar, pulling the Mustang forward. Within moments, the aircraft was airborne, climbing through the spring air over Cambridgeshire. For the next 30 minutes, Harker pushed the Mustang through its paces. He rolled it, dove it, climbed it, evaluated its handling characteristics with the practiced eye of an engineer and the instincts of a combat pilot. At low altitude, below 15,000 feet, the Mustang was extraordinary. It was 30 miles per hour faster than the Spitfire 5, despite using roughly the same power. The controls harmonized beautifully. The range was nearly double that of contemporary British fighters. Everything about the aircraft's handling suggested that North American aviation's designers had created something special, something that transcended the ordinary limitations of fighter design. Then Harker climbed higher. Above 18,000 feet, the transformation was subtle but unmistakable. The Allison engine began losing power as the thin air starved its single-stage supercharger. By 20,000 feet, the decline was pronounced. At 25,000 feet, where the Luftwaffe increasingly operated and where American heavy bombers flew their missions deep into Germany, the Mustang struggled. The performance that had seemed so exceptional at low altitude became merely adequate, then disappointing. Harker brought the Mustang back to Duxford and climbed out of the cockpit, his mind already working through the implications of what he'd just experienced. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What Harker understood in that moment would alter the course of the air war over Europe, though neither he nor anyone else at Duxford could have predicted the magnitude of that change. The Mustang's problem was not the airframe. That aerodynamic masterpiece represented the culmination of advanced American engineering, incorporating NACA laminar flow-wing sections and a cooling system so efficient it actually produced thrust. The problem was the engine, and specifically, the engine's inability to maintain power at the altitudes where the air war over Europe was increasingly being fought. On May 1, 1942, Harker sat down with pen and paper to write a report that would change aviation history. His words were measured but carried unmistakable conviction. The Mustang, he wrote, could prove itself a formidable low and medium altitude fighter. But the critical observation came next. With a powerful and good engine, like the Merlin 61, its performance could be outstanding. The Merlin 61. Those three words represented more than just an engine designation. They represented a technological revolution in supercharging that Rolls-Royce had recently achieved under the direction of Stanley Hooker, the company's brilliant supercharger specialist. The Merlin 60 series engines featured two-stage, two-speed supercharging, a complex system that compressed the air-fuel mixture twice before it entered the engine's cylinders. To understand why this mattered requires grasping the fundamental challenge of piston-engine aircraft. Power output depends on how much air an engine can consume. At sea level, where air is dense, engines breathe easily and produce their rated power. But as an aircraft climbs, the air becomes progressively thinner. By 20,000 feet, the atmospheric pressure is roughly half what it is at sea level. An engine without supercharging would lose half its power. Single-stage superchargers, like the one fitted to the Mustang's Allison engine, used a mechanically driven compressor to force more air into the engine. This worked well up to a point, typically around 15,000 feet. Above that altitude, the supercharger itself began struggling against the thin air. The engine's power output declined rapidly, and with it, the aircraft's speed, climb rate, and overall effectiveness. Two-stage supercharging solved this problem through brute force engineering elegance. The first stage compressed the incoming air. The second stage compressed it again. Between the stages, an intercooler reduced the temperature of the compressed air, preventing detonation and allowing even higher compression ratios. The result was an engine that could maintain sea-level power output far deeper into the atmosphere than any single-stage design. The Merlin 61 and its close relatives in the 60 series had been developed originally for the Wellington 6 high-altitude bomber, but when only 63 of those bombers were produced, Rolls-Royce quickly adapted the engine for the Spitfire 9. The transformation was dramatic. At 30,000 feet, a Merlin 61-powered Spitfire 9 was 70 miles per hour faster than the Mark V. The new engine didn't just improve high-altitude performance, it revolutionized it. Harker's suggestion seemed obvious in hindsight, but it faced immediate and substantial resistance. The Air Ministry in London dismissed the idea out of hand. Every available Merlin 61 engine was already allocated. Spitfires needed them desperately to counter the new Focke-Wulf 190, which had appeared over France in late 1941 and was proving devastatingly superior to the Spitfire 5. Lancaster bombers needed them to carry their heavy bomb loads deep into Germany. There simply weren't any engines to spare for experimental conversions of American fighters, no matter how promising the concept might be. But Harker was persistent, and he had allies. Ray Dorey, Rolls-Royce's head of engine flight test, supported the idea. More importantly, Air Chief Marshal Sir Wilfrid Freeman, the Air Member for Production and Research, eventually succumbed to Harker's advocacy. Freeman authorized Rolls-Royce to convert 5 Mustang airframes to Merlin power, more as an experimental program than a serious production proposal. In June 1942, 4 Mustangs arrived at Rolls-Royce's flight test facility at Hucknall. Their serial numbers were AM203, AM208, AL963, and AL975. A 5th aircraft, AM121, would join them later. These aircraft, designated Mustang X during their conversion, represented a gamble. If the conversion failed, Rolls-Royce would have wasted time and resources that could have been devoted to more conventional projects. If it succeeded, the implications could be profound. The engineering challenges were substantial but not insurmountable. The Merlin 65, chosen for the initial conversions because it was identical to the engine powering the Spitfire 9, was heavier than the Allison by more than 350 pounds. The two-stage supercharger added length and complexity. The cooling requirements far exceeded what the Mustang's original radiator system could handle. Rolls-Royce engineers studied the problem systematically. They relocated the wing slightly forward to maintain proper center of gravity with the heavier engine. They designed a distinctive chin radiator beneath the propeller spinner to handle the increased cooling demands of both the engine itself and the intercooler between the supercharger stages. They fitted a 4-bladed Rotol propeller to absorb the Merlin's greater power output. The work proceeded through the summer and into autumn. On October 13, 1942, Captain R.T. Shepard, Rolls-Royce's chief test pilot, climbed into the first converted Mustang X, AL975. He advanced the throttle, and the Merlin 65 responded with its characteristic sound, different from the Allison but unmistakably powerful. The aircraft rolled down Hucknall's runway and climbed into the October sky. What Shepard discovered during that first flight exceeded even optimistic expectations. The Mustang X flew like a completely different aircraft. In November, systematic performance testing began. The results were extraordinary. At 22,000 feet, with the supercharger in full boost, the Mustang X achieved 413 miles per hour. Later tests with AM208 pushed the maximum speed to 433 miles per hour at 22,000 feet. The absolute ceiling, the altitude at which the aircraft could no longer maintain level flight, reached 40,600 feet. These numbers represented revolutionary performance for a single engine single-seat fighter. The Mustang Mark I, with its Allison engine, managed about 390 miles per hour at 15,000 feet, then lost speed rapidly with increasing altitude. The Mustang X maintained its speed advantage deep into the stratosphere, where bomber formations flew, and where German fighters increasingly operated. But speed alone didn't tell the complete story. The Merlin-powered Mustang combined speed with the aerodynamic efficiency and fuel capacity that had characterized the original design. The result was a fighter that could fly farther and faster at high altitude than anything else in the Allied arsenal. This wasn't an incremental improvement. This was a fundamental transformation of operational capability. The British couldn't immediately capitalize on this discovery. Rolls-Royce's Merlin production was stretched to its absolute limits, supplying engines for Spitfires, Lancasters, and Mosquitoes. There was no excess capacity to re-engine the RAF's existing fleet of Allison-powered Mustangs, despite Freeman's proposal to do exactly that with 500 Merlin 65 engines. The solution came from across the Atlantic. In September 1940, before the Mustang X program even began, an agreement had been reached between Rolls-Royce and the Packard Motor Car Company to manufacture the Merlin under license in the United States. The first Packard-built engine, designated V1651, ran in August 1941. By mid-1942, Packard was producing Merlins in substantial quantities. More importantly, Packard was moving into production of the two-stage supercharged version, designated V1653, and equivalent to the British Merlin 68. The first of these sophisticated engines would roll off Packard's production lines in mid-December 1942. When North American aviation needed Merlin engines for American-built Mustangs, the supply would be available without competing with British aircraft production. The story of how North American came to embrace the Merlin-powered Mustang involves another key figure, Lieutenant Colonel Thomas Hitchcock, the U.S. Assistant Military Attaché in London. Hitchcock had already achieved considerable fame before the war as a polo player, widely regarded as the greatest the sport had ever seen. But when war came, Hitchcock found his way into military service and eventually to London, where his role involved evaluating aircraft and reporting to Washington on British aviation developments. In May 1942, Rolls-Royce informed Hitchcock about their plans to convert Mustang airframes to Merlin engines. Hitchcock, who had flown the Allison-powered Mustang and recognized both its potential and its limitations, immediately grasped the significance. He began advocating energetically through American channels, writing reports and sending recommendations to Wright Field and to North American aviation. Hitchcock's timing was fortuitous. In July 1942, North American received authorization to convert 2 Mustangs to Merlin power, using Merlin 65 engines imported from England. The aircraft, originally designated XP-78, but soon redesignated XP-51B, used airframes that had been built for the RAF but kept by the USAAF for testing. Their serial numbers were 4137-350 and 4137-421. North American's engineers approached the conversion with characteristic energy and competence. They faced the same challenges Rolls-Royce had confronted: coolant capacity, center of gravity, propeller selection, and they solved them in slightly different ways. The result was similar but not identical to the British Mustang X, reflecting American manufacturing practices and component availability. The first XP-51B flew on November 30, 1942, piloted by Bob Chilton. Just weeks after the British had proven the concept, the Americans confirmed it. The Merlin and the Mustang were a perfect match, each amplifying the other's strengths. The engine provided the high-altitude power the airframe had always been capable of exploiting. The airframe provided the aerodynamic efficiency and fuel capacity that allowed the engine's power to translate into unprecedented range and endurance. Remarkably, the U.S. Army Air Forces had already placed orders for the P-51B in August 1942, 3 months before any Merlin-engined Mustang had flown. This leap of faith reflected the desperate need for a long-range escort fighter and the confidence that British testing and American engineering could deliver it. 400 aircraft were ordered initially, a number that would grow dramatically as the program's success became evident. Production of the P-51B began at North American's Inglewood, California plant in June 1943. A second production line opened in Dallas, Texas, producing identical aircraft designated P-51C to distinguish their origin. By late summer 1943, Merlin-powered Mustangs were beginning to arrive in England, though not initially for the mission that would define their war. The first unit to receive the P-51B was the 354th Fighter Group, which arrived in England in October 1943, but the 354th was assigned to the newly organised 9th Air Force, a tactical air force being formed to support ground operations during the planned invasion of France. The 8th Air Force, which was conducting the daylight strategic bombing campaign deep into Germany, initially had no P-51 equipped units. This reflected ongoing debates within American Air Command about the best use of the new fighter. The 9th Air Force needed fighters for ground attack and close air support. The 8th Air Force already had P-47 Thunderbolts and P-38 Lightnings for bomber escort. The P-51B's superior range wasn't immediately recognized as decisive, partly because early models lacked the additional fuel tankage that would eventually give them their extraordinary endurance. On December 1, 1943, the 354th Fighter Group flew its first combat mission, a fighter sweep over France. 24 Mustangs crossed the Channel, passed over Belgium and the Calais area, and returned without encountering significant enemy opposition. One aircraft sustained minor damage from German anti-aircraft fire. The mission was uneventful, but it marked the operational debut of what would become the most important Allied fighter of the war. Within weeks, the 354th began flying escort missions, demonstrating the P-51B's potential. On December 20, 1943, Mustangs escorted bombers as far as Kiel, 480 miles inside Germany. This was deeper than P-47s could reach with existing fuel loads, and it provided the first concrete demonstration of the Merlin Mustang's strategic value. The Luftwaffe noticed immediately. A decrypted German intelligence report dated December 29, 1943, just 28 days after the first P-51B mission, described the new American fighter with remarkable accuracy. German intelligence estimated its maximum speed at 430 miles per hour at 23,000 feet, very close to the actual performance. They noted its long range, its heavy armament, and its apparent ease of handling. The report concluded that the Merlin-powered Mustang represented a formidable and potentially deadly threat. What the Germans couldn't know was that the P-51B represented only the beginning. North American engineers were already at work on improvements. A fuselage fuel tank, added behind the pilot, increased internal fuel capacity from 184 gallons to 269 gallons. External drop tanks under the wings could add another 300 gallons when two 75-gallon tanks were fitted. With this fuel load, the Mustang's range approached 2,000 miles, but the additional fuselage tank created problems. Filling it moved the aircraft's center of gravity aft, beyond acceptable limits. The Mustang became difficult to control, particularly during takeoff and initial climb when the fuselage tank was full. Pilots learned to burn fuel from the fuselage tank first, restoring proper balance before entering combat. This awkward procedure was accepted as necessary because the alternative, limited range, was unacceptable for the mission's 8th Air Force needed to fly. The strategic situation over Germany in late 1943 and early 1944 was approaching a crisis for the American daylight bombing campaign. The 8th Air Force had committed to destroying Germany's industrial capacity through precision daylight bombing, but the casualties were becoming unsustainable. German fighter pilots, many of them veterans with years of combat experience, were inflicting devastating losses on American bomber formations. On August 17, 1943, the 8th Air Force attempted to destroy the ball-bearing factories at Schweinfurt, deep inside Germany. The raid was an audacious disaster. Of 230 bombers dispatched, 60 were completely destroyed and many others damaged so severely they would never fly again. The loss rate exceeded 25%. No military force could sustain such casualties indefinitely. The fundamental problem was simple. Existing Escort fighters lacked the range to accompany bombers throughout their missions into Germany. P-47 Thunderbolts could reach into France and Western Germany before turning back. P-38 Lightnings had better range but suffered reliability problems in the cold air at altitude. Beyond the range of friendly fighters, bombers flew unescorted, and German fighters waited until the escorts turned back before attacking. The Merlin-powered Mustang solved this problem completely. With full internal and external fuel, a P-51B could escort bombers all the way to Berlin and return to England with fuel remaining. This capability fundamentally altered the strategic equation. German fighters could no longer simply wait for escorts to depart. They had to fight their way through American fighters to reach the bombers, and increasingly, they discovered they couldn't. By February 1944, P-51-equipped units of the 8th Air Force were flying escort missions deep into Germany. The transformation in bomber loss rates was immediate and dramatic. In October 1943, before Merlin Mustangs arrived in quantity, bomber loss rates averaged 9.1% of aircraft attacking their targets, with another 45.6% returning damaged. By February 1944, loss rates had fallen to 3.5%, with 29.9% damaged. These numbers represented more than statistics. They represented crews who survived missions that would have killed them months earlier. They represented bombers that completed their missions and returned to fly again. They represented the beginning of the end for the Luftwaffe's ability to defend German airspace. On March 4, 1944, the 4th Fighter Group flew the first P-51 escort mission all the way to Berlin. The symbolism was profound. Berlin, the capital of the Third Reich, the heart of Nazi Germany, was now vulnerable to American daylight bombing. Hermann Göring, commander of the Luftwaffe, would later testify at Nuremberg that when he saw Allied fighters over Berlin, he knew the war was lost. But the operational reality was more complex than simple symbolism. The P-51B didn't just provide range, it provided performance that German fighters struggled to match. At 25,000 feet, where bomber formations typically flew, a Merlin-powered Mustang could achieve 440 miles per hour. The Messerschmitt Bf 109G, the Luftwaffe's frontline fighter, managed about 386 miles per hour at that altitude. The Focke-Wulf FW-190A reached 408 miles per hour under optimal conditions. This speed advantage proved tactically decisive. American pilots could choose when to engage and when to disengage. If a combat situation looked favorable, Mustang pilots could pursue aggressively. If circumstances turned against them, they could accelerate away from German fighters that lacked the speed to follow. The Germans couldn't force combat on Mustangs whose pilots chose to avoid it. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Mustang's advantages extended beyond raw speed. The two-stage Merlin maintained power output at altitudes where single-stage German engines gasped for air. Climb rate remained excellent up to 30,000 feet and beyond. The aircraft could dive at high speed without the control stiffening that plagued many fighters. The harmonized controls responded crisply across the entire speed range. German pilots who encountered Merlin Mustangs in combat quickly learned to respect and fear them. Combat reports from early 1944 describe American fighters that seemed to have unlimited performance margins, that could accelerate away from any pursuit, that could climb faster than anything the Luftwaffe could field. These weren't the P-47 Thunderbolts German pilots had learned to engage on favorable terms, nor were they the troubled P-38s that sometimes fell victim to their own temperamental engines. The psychological impact was profound. Luftwaffe pilots, already outnumbered and facing increasingly inexperienced replacements as veteran pilots were killed, now confronted escorts that were simply better than their own aircraft in the performance categories that mattered most. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The tactical situation forced German commanders into an impossible dilemma. They could refuse combat, preserving their aircraft and pilots, but allowing American bombers to strike targets unopposed. Or they could engage, accepting heavy casualties in exchanges where American numerical and performance advantages proved overwhelming. Neither option offered acceptable outcomes. Between January and April 1944, the Luftwaffe lost more than 1,000 fighter pilots. 28 of these had more than 30 confirmed victories. 8 had more than 100. These weren't novices being lost. These were the veterans, the experienced pilots whose knowledge and skill had made the Luftwaffe formidable. Their deaths created holes in German fighter formations that could never be adequately filled. The Merlin engine's two-stage supercharger was the key to all of this. The first stage, driven through reduction gearing at 6.39 1-to-1 ratio, compressed the incoming air-fuel mixture. The compressed mixture passed through the intercooler, where ethylene glycol coolant reduced its temperature. The second stage, which could be engaged at higher altitudes through hydraulic clutches controlled by electric solenoids, compressed the mixture again, this time at 8.09 5-to-1 ratio in high-speed blower position. The result was manifold pressure that remained adequate for full power output far higher into the atmosphere than any single-stage design could achieve. At 25,000 feet, the Packard V16-53 Merlin generated approximately 1,500 horsepower at military power settings. At war emergency power, using higher boost pressures and fuel enrichment, output exceeded 1,600 horsepower. This power, combined with the Mustang's aerodynamically efficient airframe, produced performance that seemed almost miraculous to pilots who had flown earlier fighters. Colonel Clarence Bud Anderson, who would become a Mustang ace, later wrote that the aircraft went like hell because the Merlin had great gobs of power and was equally at home high or low, thanks to its two-stage, two-speed supercharger. The operational range particularly impressed American commanders. Brigadier General Thomas "Tommy" Hayes, who flew Mustangs in combat, stated that the Merlin-powered P-51 had the three qualities you need most if you were going to escort bombers to Berlin: range, range, and range. This wasn't hyperbole. It was operational reality expressed by someone who understood what long-range escort meant in practice. The Mustang achieved this range through brutal efficiency. While the P-47 Thunderbolt consumed fuel at rates exceeding 5 gallons per minute at combat power, the Merlin-powered Mustang managed roughly 3.3 miles per gallon of aviation gasoline. The difference accumulated across hours of flight time, translating directly into operational radius. Part of this efficiency came from the Merlin's sophisticated fuel management systems. The Stromberg carburetor, mounted updraft on top of the supercharger, featured automatic mixture control that optimized fuel consumption based on altitude and power settings. Pilots could lean the mixture for cruise flight, stretching range even further. The engine's relatively modest displacement, 27 litres compared to the Thunderbolt's massive 46-litre radial, meant less fuel consumed per revolution, even at high power output. But efficiency alone didn't win the air war. What mattered was the combination of efficiency and performance, range and speed, endurance and capability. The Merlin-powered Mustang delivered all of these attributes simultaneously in a package that could be produced in large quantities with reasonable reliability and acceptable maintenance requirements. Production ramped up through late 1943 and into 1944. North American's two factories produced nearly 2,000 P-51Bs and 1,750 P-51Cs before production shifted to the improved P-51D model with its bubble canopy and 6 machine guns. The RAF received 308 P-51Bs and 636 P-51Cs, designated Mustang Mark III in British service. The transformation of the Mustang from a disappointing high-altitude performer into the dominant fighter over Europe happened because one test pilot spent 30 minutes flying an aircraft in April 1942 and had the insight to recognize what a different engine could achieve. Ronald Harker's suggestion to mate the Mustang airframe with the Merlin engine represents one of the most consequential engineering decisions of the Second World War. Continuing with Part 2 of the script, the engineering that made this transformation possible deserves closer examination. Because the Merlin 60 series engines represented years of accumulated development work by Rolls-Royce's engineering staff, guided increasingly by Stanley Hooker's supercharger expertise. Hooker had joined Rolls-Royce in 1938, bringing mathematical rigor to what had previously been more art than science in supercharger design. Superchargers worked by accelerating air through a rotating impeller, converting velocity into pressure through careful management of airflow. The efficiency of this process depended on impeller design, the shape of the inlet passages, the geometry of the diffuser that slowed the air and converted kinetic energy into pressure, and dozens of other variables that Hooker systematically optimized through calculation and testing. The single-stage superchargers used in early Merlin engines and in the Allison V1710 featured one impeller, driven through reduction gearing from the engine's crankshaft. This worked adequately up to medium altitudes, but the relationship between boost pressure and altitude was fundamentally limited. As atmospheric pressure decreased with altitude, the supercharger had to work progressively harder to maintain manifold pressure in the engine's intake. Eventually, even spinning at maximum speed, the impeller couldn't provide adequate boost. Two-stage supercharging broke this limitation by staging the compression. The first stage compressed the air to an intermediate pressure. The intercooler between stages reduced temperature, increasing air density and preventing detonation. The second stage compressed the already compressed air to final manifold pressure. The result was boost pressure that could be maintained to much higher altitudes than any single-stage design could achieve. But two-stage supercharging came with costs. The additional impeller, intercooler, and associated ducting added weight and complexity. The supercharger absorbed significant power from the engine, power that wasn't available at the propeller. In the Merlin 60 series, the supercharger consumed roughly 200 horsepower at maximum boost, a parasitic loss that had to be accepted to gain high-altitude performance. The intercooler was critical to making the system work. Compressing air heats it. The first stage impeller raised the temperature of the air-fuel mixture to levels that would cause detonation if fed directly into the second stage and then into the engine's cylinders. The intercooler, essentially a small radiator installed in the wheelcase housing between the two impeller stages, circulated ethylene glycol coolant to remove this heat. Without the intercooler, the temperature of the compressed mixture could reach 400 degrees Fahrenheit. With proper intercooling, this was reduced to levels the engine could tolerate without detonation even at high boost pressures. An additional aftercooler, positioned between the supercharger outlet and the intake manifold, provided further cooling. The Mustang's distinctive chin radiator housed not just the engine coolant radiator but also the aftercooler, managing thermal loads that the original Allison installation had never required. The two-speed feature of the Merlin supercharger added another layer of sophistication. At low and medium altitudes, the supercharger operated in low gear at the 6.39 1-to-1 ratio. This provided adequate boost without excessive parasitic power loss. As the aircraft climbed above approximately 20,000 feet, hydraulic clutches engaged to shift the supercharger into high gear at 8.095-to-1 ratio. The transition happened automatically based on altitude, though pilots could override it manually if tactical situations required. This automatic gear change represented remarkable engineering for 1942 technology. The system had to function reliably despite the vibration, temperature extremes, and G-forces of combat flight. Hydraulic fluid had to remain fluid at -40 degrees Fahrenheit at altitude. Clutches had to engage smoothly without jerking the engine. The control system had to respond quickly enough that pilots didn't notice the transition during combat maneuvering. Packard's licensed production of these complex engines deserves recognition as an industrial achievement in its own right. Rolls-Royce had built the Merlin's design around British manufacturing practices, British materials specifications, and British measurement standards. Packard had to convert everything to American equivalents while maintaining the precision necessary for high-performance aero engines. The conversion process wasn't simply a matter of changing inches to millimeters or vice versa. British engineering drawings used different conventions for thread specifications, surface finishes, material grades, and tolerances. Some components had to be redesigned entirely to accommodate American manufacturing equipment and processes. Yet Packard managed to produce engines that were functionally identical to British-built Merlins, maintaining the performance characteristics and reliability that made the engine successful. One significant American improvement involved the main bearings. Packard changed from the copper lead alloy used in British Merlins to a silver lead combination with indium plating. This modification, developed by General Motors' Pontiac division, prevented corrosion from lubricating oils and improved break-in characteristics and load-carrying capacity. British engineers assigned to Packard were initially skeptical of the change, but tear-down inspections after rigorous testing convinced them that the American bearing design offered decided advantages. By mid-1943, Packard was producing hundreds of V1653 engines monthly, with production ramping toward peak output of over 1,000 engines per month by 1944. This volume of production supplied not just American P-51 Mustangs, but also Canadian-built Lancaster bombers and other aircraft that required the two-stage Merlin's high-altitude performance. The operational implications of having this engine available in large quantities transformed American strategic options. In early 1943, before Merlin Mustangs appeared in numbers, the 8th Air Force faced a fundamental problem. German fighter production was actually increasing despite intensive Allied bombing. Luftwaffe pilots were inflicting unsustainable losses on American bomber formations during unescorted portions of deep penetration raids. The entire strategic bombing campaign faced potential failure. The solution wasn't primarily about destroying German aircraft factories, though that remained an objective. The solution was about killing German pilots faster than they could be replaced, and forcing the Luftwaffe into defensive battles where American numerical advantages and increasingly superior equipment would prove decisive. The Merlin-powered Mustang gave American commanders the tool to implement this strategy. By February 1944, multiple P-51-equipped fighter groups were operational with the 8th Air Force. The transformation in tactical approach was immediate. Rather than flying close escort, staying tight with bomber formations, Mustang pilots were encouraged to range ahead and to the flanks, seeking out German fighters before they could attack the bombers. When German fighters were sighted, Mustang pilots were ordered to engage aggressively, to pursue fleeing enemy aircraft. To maintain pressure, this represented a fundamental shift from defensive to offensive escort tactics. The objective wasn't just protecting bombers by staying close to them. The objective was destroying German fighters, killing German pilots, and systematically dismantling the Luftwaffe's ability to contest American control of German airspace. The Merlin Mustang's performance advantages made these aggressive tactics viable. Pilots could pursue German fighters with confidence that their aircraft's speed and climb rate would allow them to catch anything they chased. The week of February 20th through February 26, 1944, later called Big Week, demonstrated the new tactical reality. The 8th Air Force, joined by the 15th Air Force operating from Italy, launched a coordinated offensive against German aircraft production facilities. Over 6 days, more than 3,300 heavy bomber sorties struck targets across Germany, escorted by fighters, including substantial numbers of P-51 Mustangs. The results were devastating for the Luftwaffe. American fighters destroyed 17% of Germany's experienced fighter pilots in air-to-air combat during that 1 week. German fighter production facilities suffered heavy damage. More importantly, German fighter pilots discovered that they could no longer effectively defend their own aircraft factories against American attacks. The psychological impact of this failure resonated throughout the Luftwaffe. The Mustang pilots who flew these missions experienced the aircraft's capabilities firsthand through hundreds of hours of combat flying. They learned to manage the fuselage fuel tank by burning it first, restoring proper center of gravity before entering combat. They learned to use the Merlin's power to maintain energy in combat, converting speed to altitude and altitude back to speed in the continuous cycle of energy management that characterized successful fighter tactics. They learned that the Mustang excelled in certain types of combat and struggled in others. In high-speed slashing attacks and diving pursuits, the P-51 dominated. In sustained low-speed turning fights, the lighter and more maneuverable Messerschmitt Bf 109G retained advantages. But Mustang pilots could simply refuse turning engagements. using superior speed and climb to reset the tactical situation on favorable terms. German pilots who survived encounters with Merlin Mustangs reported performance that seemed to exceed reasonable expectations. Intelligence officers collecting these reports initially dismissed them as exaggerations born from stress and defeat. But as the reports accumulated from different units, different pilots, and different combat situations, the pattern became undeniable. The Americans had deployed a fighter that was simply better than anything the Luftwaffe could field in the performance categories that mattered most at the altitudes where combat occurred. Some Luftwaffe veterans who tested captured Mustangs after the war spoke candidly about the experience. Gerhard Barkhorn, who flew Messerschmitt fighters on the Eastern Front and achieved 275 confirmed victories, later tested a P-51 and acknowledged being impressed by its speed, climb capability, and high-altitude performance. The Mustang wasn't perfect, but its advantages in the critical areas were substantial and undeniable. The captured Mustang program, operated by the Luftwaffe's Circus Rosarius, provided German pilots with direct experience flying American fighters. Several P-51Bs and Cs ended up in German hands through forced landings in occupied territory or German-controlled areas. These aircraft were repaired using cannibalized parts from other crashed Mustangs, repainted with German markings and bright yellow identification paint, and flown by experienced German test pilots. The demonstrations at operational Luftwaffe bases allowed frontline pilots to see Mustang performance firsthand and to fly mock combat against them. The lessons learned were sobering. German pilots discovered that engaging a properly flown Mustang at high altitude was extremely difficult. The American fighter could simply accelerate away from any pursuit. If German pilots tried to climb to altitude advantage before attacking, the Mustang outclimbed them. If they attempted to dive away from unfavorable engagements, the Mustang followed with ease. These demonstrations provided valuable tactical intelligence, but offered no solutions to the fundamental problem. German fighters, powered by engines with single-stage superchargers or less sophisticated two-stage systems, simply couldn't match the Merlin Mustang's performance above 20,000 feet. No amount of pilot skill or tactical cleverness could overcome this equipment disadvantage when American pilots flew with reasonable competence. The Merlin engine's reliability proved another significant advantage. While no combat aircraft engine of the era was trouble-free, the Merlin established a reputation for running consistently and predictably when properly maintained. The two-stage supercharger added complexity but didn't dramatically reduce reliability. Engines typically ran for hundreds of hours between major overhauls, and catastrophic failures were relatively uncommon if pilots followed proper operating procedures. This reliability translated directly into operational availability. Fighter groups equipped with Merlin Mustangs could launch large formations with confidence that most aircraft would complete their missions without mechanical failures. Ground crews learned to maintain the engines efficiently, developing procedures for routine inspections, spark plug changes, and minor repairs that kept aircraft flying. The contrast with some German engines was striking. The Daimler-Benz DB605, which powered later marks of the Messerschmitt Bf 109, suffered increasing quality problems during 1944 and 1945, as German industry struggled with material shortages, dispersed production to avoid bombing, and increasing use of forced labor. Engine failures became more common. Time between overhauls decreased. The industrial base that had produced sophisticated engines early in the war was literally being destroyed by the bombing campaign those engines were meant to defend against. The fuel situation added another dimension to Germany's problems. The Merlin ran on 100-octane aviation gasoline, which American refineries produced in enormous quantities. By 1944, the Allies were introducing 150-grade fuel with even higher performance numbers, allowing increased boost pressures and higher power output. German synthetic fuel production, based on converting coal to liquid fuels through the Burgess process, struggled to produce adequate quantities even of lower-grade fuels. German fighters typically operated on B4 fuel, rated at approximately 87 octane, or C3 fuel, roughly equivalent to Allied 100 grade, but available in limited quantities. By late 1944, Allied bombing of synthetic fuel plants had reduced German aviation fuel production catastrophically. Luftwaffe fighter units received insufficient fuel for adequate training of replacement pilots. Some experienced pilots sat, grounded for lack of fuel, while American fighters ranged across German skies almost unopposed. The strategic bombing campaign that the Merlin Mustang enabled proved decisive not primarily through destruction of factories, but through forcing Germany into an attrition battle it couldn't win. Every mission deep into Germany forced the Luftwaffe to respond or concede control of its own airspace. When they responded, they lost pilots and aircraft faster than replacements arrived. When they didn't respond, American bombers struck targets that degraded Germany's ability to continue fighting. By March 1944, American fighters had achieved practical air superiority over most of Germany. Luftwaffe fighter forces still existed and occasionally achieved local successes, but they could no longer systematically defend German industry or German cities from daylight attack. The transformation from the dark days of Schweinfurt in August 1943 to air superiority in March 1944 took only 7 months, and the Merlin-powered Mustang was the key enabling factor. The numbers tell the story with brutal clarity. In the 10 months from June 1943 to March 1944, American heavy bombers flew approximately 86,000 sorties over Europe. They lost approximately 2,300 aircraft, a loss rate of roughly 2.7%. Between April 1944 and May 1945, after Merlin Mustangs appeared in force, bombers flew approximately 200,000 sorties and lost approximately 3,000 aircraft, a loss rate of roughly 1.5%. The reduction in loss rates meant that bomber crews had substantially better chances of surviving their required tour of 25 missions, later increased to 30, and then 35. Early in the campaign, the statistical probability of completing a tour approached 0. By late 1944, most crews could reasonably expect to survive if they flew carefully and received reasonable luck. This transformation in survival probability directly affected morale, recruitment, and the entire sustainability of the strategic bombing campaign. Fighter pilots flying Merlin Mustangs claimed approximately 4,950 enemy aircraft destroyed in air combat during the war, with another 4,131 destroyed on the ground. These numbers represented not just machines destroyed, but also pilots killed or captured, experience lost, and German industrial capacity wasted building replacements that would themselves be destroyed before achieving strategic effect. The quality of German replacement pilots declined catastrophically during 1944. Early in the war, Luftwaffe pilots received thorough training, including hundreds of hours of flight time before reaching operational units. By late 1944, fuel shortages had forced dramatic reductions in training. Replacement pilots sometimes arrived at frontline units with barely 100 hours total flight time, minimal combat training, and often no instrument training whatsoever. These inadequately prepared pilots faced veteran American pilots flying objectively superior aircraft. The resulting casualty rates were grimly predictable. New German pilots survived on average only a handful of missions before being shot down. The few who survived their first combats and learned the necessary survival skills became valuable precisely because they were so rare. But even experienced German pilots couldn't overcome the performance gap when flying inferior aircraft against numerically superior opponents. The Merlin engine's contribution to this outcome cannot be overstated. The two-stage supercharger was the critical technology that enabled the Mustang to perform at the altitudes where the war was fought. Without it, the P-51 would have remained a capable low-altitude fighter with excellent range but inadequate high-altitude performance. With it, the Mustang became the dominant fighter over Europe. Stanley Hooker's supercharger development work at Rolls-Royce provided the foundation. Packard's successful licensed production provided the volume. North American's excellent airframe provided the platform. But the synthesis of these elements into a single aircraft required insight, and that insight came from Ronald Harker's 30-minute flight in April 1942 and his recognition that the Mustang's airframe deserved a better engine. The story of how a British test pilot, flying an American fighter, recognized that a British engine could transform its performance, leading to American mass production of both engine and airframe, exemplifies the Allied collaboration that characterized the war effort. No single nation alone possessed all the necessary elements. Britain had the engine technology. America had the manufacturing capacity and the airframe design. Together, they created a weapon system that proved decisive. Lieutenant Colonel Thomas Hitchcock's role in advocating for the Merlin Mustang and shepherding its adoption by American forces proved equally critical. Hitchcock's reports to Washington, his persistent advocacy, and his personal commitment to making the program succeed helped overcome institutional resistance and bureaucratic inertia. His death in April 1944, during a test flight investigating problems with the fuselage fuel tank installation, came just as the aircraft he had championed was proving its worth over Germany. Hitchcock never saw the P-51D, the ultimate development of the Merlin Mustang concept, with its bubble canopy providing exceptional visibility and 650 caliber machine guns providing heavier firepower. He never saw the Mustang operating from Iwo Jima to escort B-29 superfortresses to Japan. He never saw the post-war racing Mustangs or the civilian warbird, a movement that keeps the type flying decades after the war ended. But he saw enough to know that his advocacy had been justified. By D-Day, June 6, 1944, the 8th Air Force's fighter groups were predominantly equipped with Merlin-powered Mustangs. 14 of 15 fighter groups flew P-51s by the end of 1944. The transformation from the dark days of 1943, when the strategic bombing campaign teetered on the edge of failure, to total air superiority in 1944 and 1945 was complete. The Luftwaffe made one final desperate attempt to contest Allied air superiority during Operation Bodenplatte on January 1, 1945. German fighters launched mass attacks against Allied airfields in Belgium, France, and Holland, achieving surprise and destroying substantial numbers of Allied aircraft on the ground. But the Germans lost approximately 300 aircraft and, more critically, several dozen experienced pilots, including unit commanders. The ratio of loss was unsustainable, and Bodenplatte effectively marked the end of the Luftwaffe as a coherent fighting force. For the remaining months of the war, Allied fighters, including Merlin Mustangs, ranged across Germany almost unopposed. They strafed German airfields, destroying aircraft on the ground. They attacked trains, vehicles, and troops. They escorted bombers that struck targets throughout Germany with near impunity. The Luftwaffe occasionally contested these operations, but could no longer systematically defend German airspace. The Merlin engine that made this possible continued evolving through the war. Later versions ran on 150-grade fuel, allowing boost pressures up to 25 pounds per square inch above atmospheric pressure and power outputs exceeding 2,000 horsepower. These engines powered the P-51H, the ultimate Mustang variant, which achieved speeds approaching 490 miles per hour. But the P-51H arrived too late to see combat in World War II. The legacy of the Merlin-powered Mustang extended well beyond the war. The aircraft served with air forces around the world into the 1950s and 60s. In Korea, redesignated 51, Mustangs flew ground attack missions with distinction. In civilian hands, Mustangs became sought-after warbirds and air racing aircraft. Modified Mustangs set speed records and won races. The type's performance, even by modern standards, commands respect. But the historical significance transcends the aircraft's specifications or combat record. The Merlin-powered Mustang represents the moment when Allied industrial and technological capabilities crystallized into practical air superiority over Germany. It represents the solution to a strategic problem that threatened to derail the entire Allied war effort. It represents collaboration between British and American aviation industries at the highest levels of sophistication. Most fundamentally, it represents what happens when excellent engineering recognizes opportunity. The Mustang's airframe had always been capable of exceptional performance. The Merlin 60 series engine had always been capable of providing high-altitude power. What was needed was someone to recognize that these two elements belonged together, and that someone was Ronald Harker on April 30, 1942, after 30 minutes in the cockpit of an Allison-powered Mustang over Cambridgeshire. The two-stage, two-speed supercharged Merlin transformed the Mustang from a promising but limited design into the fighter that won air superiority over Europe. The complex impellers spinning at thousands of revolutions per minute, the intercooler managing temperatures that could destroy engines, the hydraulic clutches engaging at altitude to shift supercharger gears, all of this sophisticated engineering translated into manifold pressure, horsepower, and ultimately into speed and altitude performance that German fighters couldn't match. German engineers understood supercharging. They had developed sophisticated systems for their own engines, but Germany's strategic situation, resource constraints, and industrial dispersal to avoid bombing prevented development and production of engines that could compete with the Merlin 60 series. The DB605 engines that powered late-war Messerschmitts used single-stage superchargers. Some BMW 801 engines in Focke-Wulf 190s featured relatively sophisticated two-stage systems, but these were heavier, more complex, and less effective than the Merlin's design. The industrial capacity to produce sophisticated engines in large quantities proved as important as the engineering that created them. Packard's production of V1650 engines exceeded 12,000 per month at peak, supplying not just Mustangs but also other aircraft types. German engine production, despite impressive efforts under increasingly difficult circumstances, never approached this volume for comparable engines. The contrast between Allied and German situations in late 1944 illustrates the compounding effects of air superiority. Allied factories operated without interference, producing aircraft and engines in enormous quantities. German factories operated under constant threat of bombing, with production dispersed, quality declining, and experienced workers increasingly scarce. Allied pilots trained with adequate fuel, receiving thorough instruction. German pilots trained with minimal fuel, arriving at operational units inadequately prepared. Allied aircraft received proper maintenance with genuine spare parts. German aircraft struggled with ersatz materials and undertrained ground crews. In this context, the Merlin-powered Mustang was both cause and symptom of Allied advantages. It enabled air superiority, and it benefited from the industrial capacity that air superiority protected. The positive feedback loop, where success enabled more success, characterized the entire strategic situation in Europe from mid-1944 onward. The story concludes not with the war's end, but with the recognition that technological advantage in war often comes not from revolutionary new inventions, but from recognizing how existing technologies can be combined in new ways. The Mustang airframe existed. The Merlin engine existed. What didn't exist, until Ronald Harker suggested it, was the combination. That combination, enabled by Packard's production capacity, championed by Thomas Hitchcock, and proven by thousands of pilots who flew combat missions over Europe, changed the course of the air war. The Germans never expected that a British engine could turn an American fighter into a 440-mile-per-hour interceptor that could escort bombers to Berlin and defeat the Luftwaffe in its own skies. But that's exactly what happened, and the two-stage, two-speed supercharged Merlin made it possible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.